I want to talk to you today about the need to evaluate physical mechanisms that are associated with downscale future climate change patterns. And this is, we've been thinking at UCLA a lot about uncertainty related to climate change projections and actually how you bring these course evolution GCM projections down to scale in a way that's credible and also provides information about uncertainty. So we're preoccupied with the question of how we can increase confidence in high-resolution projections of future climate, and how we can downscale the GCMs efficiently so as to map out the uncertainty space that is associated with very considerable GCM spreads that I'm sure you're all aware of. And so to address these questions, I'll be discussing some examples from our recent work at UCLA. And although I will give you some information about the technical aspects of the work that we've been doing, I'm going to avoid the details because I think this is a pretty broad audience here. And then I'll be focusing on the most important aspects for the questions that I have listed above, these two questions. All right, so we have been doing something that we call hybrid downscaling. It's not quite as catchy a name as LOCA, but we call this hybrid dynamical physical downscaling. I should launch a naming contest for this method so that we can look for something more punchy. And the essence of this technique is to do very limited dynamical downscaling for a particular region, and then develop some very simple mathematical or statistical models to mimic the dynamical model behavior. So it's both dynamical and statistical in the sense that we first do dynamical downscaling, and then we try to model the dynamical model behavior with very simple models. And then we can use these statistical models to produce regional data that corresponds to any GCM for any time slice and for any forcing scenario. And as we will see, the hybrid downscaling forces the practitioner or the researcher to diagnose and understand the climate change patterns that are produced by dynamical downscaling. This is very important. We actually have to analyze the data and understand it to produce the ultimate model that we use for the downscaling. This method also avoids what's known as the stationarity assumption, which is an issue with the statistical methods where an assumption is made about the relationship between the large scale and the small scale, which may or may not hold as you go forward. And this method also allows for characterization of the full uncertainty associated with GCM spread and forcing scenarios. That's a very brief overview of this method. And we have applied this method to California's Sierra Nevada. So I'm just going to walk you through an example of an application. So the first step, as I mentioned, is to do dynamical downscaling. You already defined this. Basically, you're using a numerical model of the climate system over a limited area, and you are feeding that model information from the GCMs and recovering the fine-scale information that is consistent with that coarse resolution GCM output by solving the actual equations of the atmosphere. So we did the dynamical downscaling with a 2-kilometer resolution grid over the Sierra Nevada, which is shown here. And there are a couple place names on there. And we did a baseline run, which covers the period 1981 to 2000. And we did future runs, 2081 to 2100, driven by 5 GCMs under the RCP 8.5 forcing scenario. CMIP 5, of course, is the latest ensemble of global climate models, and RCP 8.5 is the so-called business as usual forcing scenario. All right, so here are some example warming patterns for 5 selected months, which span the most important phase of the annual cycle for water resources in California, November, January, March, May, and July. And these are just what these warming patterns look like for this end-of-century time slice. And this is the average over all 5 dynamical downscaled features. And the warming patterns are very similar for individual simulations, even if the magnitudes actually vary somewhat. And there are 2 features that I want to call your attention to in these patterns. One is that the warming is greater on the continental side of the Sierra Nevada. So if you look on the right-hand side, in all the months, you can see more warming on that side than you see in the Central Valley. And the second thing that you notice is that the imprint of a process known as snow albedo feedback is very clear in every month. Snow albedo feedback is a climate feedback process. When snow retreats, it reveals a land surface that is much reflective of sunshine, and that actually amplifies the warming because of greater absorption of solar radiation in those areas. And so you can see an amplification of warming in these areas where snow is retreating. And we can see this pattern very, very clearly if you actually look at the areas where the snow is changing. So the bottom 5 panels here are just showing you the change in the fractional area coverage of snow. And you can see that these areas where the snow is retreating correspond very closely to the areas where you have the most warming in the Sierra Nevada. So you can see very clear evidence of the snow albedo feedback process going on. All right, so that is an overview of some of the results from step 1 of this hybrid downscaling process. Step 2 is to construct and apply statistical models to model the dynamical model behavior. So based on these results, we can construct a very simple mathematical model that takes as inputs the main drivers of regional warming. And then through very careful diagnostics, we determine that these drivers are, first of all, the overall GTM warming in the region. So if you know the overall GTM warming in the Sierra Nevada region, that gives you a pretty good sense of what the average warming is going to be when you actually do dynamical downscaling. In addition, if you know the GTM warming contrast between North America and the adjacent Pacific Ocean, that helps you scale the contrast that I mentioned between the east and west of the Sierra Nevada. And GTMs generally produce more warming in the interior of continents than they do over the oceans. This warming contrast is an important feature of global climate change, but the degree of contrast varies across GTMs. And then finally, snow albedo feedback is the third process that actually influences these warming patterns rather dramatically. So these are the 3 drivers of the warming patterns. And so you can take these as inputs, and you can build a statistical model that produces warming patterns that mimic those of the dynamical model, which in this case is WRF. So this is the elevation now as a function of, this is the warming rather, as a function of elevation for 2 months, March and June. So on the x-axis here is the warming, on the y-axis is the elevation. And I'm showing here both the dynamical results and the results from the statistical model that was built to mimic the dynamical model. And you can see that those 2 agree extremely well. This indicates that we can model the dynamical model's warming patterns very well if we know these 3 factors: how much warming a GTM gives, how much land sea contrast that GTM has, and how much snow albedo feedback the regional model actually produces. So this simple model can now be used to produce warming patterns that we would have produced had we downscaled all the available GTMs with dynamical techniques, which are very expensive. So now we have a kind of a shortcut that allows us to scale up, if you will, the dynamical downscaling. So here is the warming now as a function of elevation from October through July. So I'm just going through all these months, October all the way through the midsummer. And the solid red line is now the ensemble mean of the GCMs. And the red shading is an indication of uncertainty that is associated with GCM spread. So now we have an ensemble mean outcome for the GCMs, and we have an indication of spread. And this is the uncertainty exploration that is now common practice in the global modeling community, which is to actually acknowledge that GCMs give different outcomes. And you can note that there's this warming bulge that's associated with snow albedo feedback. It moves to higher elevations with the seasonal retreat of the snow line. So if you look throughout the calendar year as you go forward, which is going down in this plot, you can see that the warming maximum is going up in elevation as the snow is retreating. And that's an indication of the snow albedo feedback process that I mentioned earlier. All right, so how do these projections stack up against other downscale data products? Here again is the warming that's produced by this hybrid approach as a function of elevation for these 2 months, March and June. Let's now overlay the warming that's produced by 2 commonly used downscaling techniques. So here is the warming that's given by DCSD, which may actually be one of the most commonly applied downscaling techniques. This database is available for the entire country, and people are using it all the time for all kinds of applications. And you can see that it's actually rather different from the warming produced by the hybrid approach. Here's another technique. This is DCCA. This is the warming given by this technique. In the green curve there, if you can see it, and if you can see that green curve, it's actually also rather different from the hybrid technique. So neither BCFD nor BCCA captures the large variations in warming with elevation. And these variations in warming with elevation are related to snow albedo feedback, as I mentioned before. In fact, both of these techniques produce rather flat warming projections in the Sierra Nevada with very little spatial structure. So here again are the dynamically downscaled warming patterns for 5 months. You've seen these patterns before. This is November, January, March, May, and July. And this is the warming patterns that are produced by these two techniques, BCCA and BCFD. And you can see that compared to the hybrid approach, you really get a rather flat warming pattern. In fact, the BCFD technique is almost identical to the DCM warming pattern. So even though that's billed as downscaling, it's actually not adding any additional spatial structure from what you actually get from the GCM output. So there's a little bit of a buyer beware element to these downscaling methods. Does this matter? We have used this hybrid approach to produce projections for other variables. Here is the end-of-century RCP 8.5 advance and runoff timing in the Sierra Nevada as a function of elevation. And what's being shown here is the runoff centroid date, R50. This is a key metric for water resource management and planning in California and elsewhere. This is basically the date by which half of the water has run off. And this advances in the future, mainly because of the melting of snow. The red line here is the ensemble mean, that's the solid line, and the dashed lines are indicating uncertainty due to DCM spread. And this is an advance in this R50, so the numbers are negative, and they start at 0 on the right and get more and more negative as you go to the left. So that's an indication of an advance in snow and runoff. And then the gray shaded area on there, which shows the magnitude of baseline natural variability in R50. So one of the other themes that has emerged from the climate literature in the past maybe 5 years or so is how important natural variability is in uncertainty. So we wanted to actually look at how much variability is compared to these signals. And you can see that the ensemble mean advance in R50 is very significant compared to the natural variability. And even if you take into account the GCM spread, you see a pretty large signal in this particular metric compared to natural variability. So there's this is showing that there should be a pretty big shift in R50 going forward. There's a dramatic change in runoff timing portrayed here, and there are certain elevations that are affected more than others. And in fact, those certain elevations happen to be those that are very much affected by snow albedo feedback, this process that I mentioned earlier. All right, what about the other forcing scenarios? The IPCC has mandated the use of forcing scenarios that are somewhat milder than the business as usual scenario. So we have RCP 6.0, which is the orange, RCP 4.5, which is the lighter blue, and RCP 2.6, which is the darker blue. RCP 2.6 is the scenario that involves a pretty dramatic ramp down in carbon emissions over, beginning in 2005, and that didn't happen. So RCP 2.6 is looking like a kind of a wildly optimistic forcing scenario. And you can see that no matter which forcing scenario you choose, a pretty significant change in runoff is apparent at precisely those elevations where the snow albedo feedback process most amplifies warming. And so if you look at RCP 4.5, which is looking like now a much more realistic mitigation scenario, you still see significant changes in runoff compared to the natural variability. So what this means is that a significant change in runoff timing for watersheds draining certain elevations is inevitable, no matter which forcing scenario you choose and no matter which GCN you choose, you still get a large change in runoff timing in these areas where slow beat of feedback is operating. And that's a rather strong conclusion. And so this technique has allowed us to reach an important conclusion about the inevitability of changes in water resources in the Sierra Nevada. Okay, I'm actually, that's conclusion, so I'm going to finish early. All right, so to conclude, to have confidence in high-resolution climate projections used for decision-making, it is critical to evaluate the physical mechanisms that underpin regional change patterns. And this is actually standard practice in the global climate modeling community. Many of the ideas, or all the ideas really that we believe in about climate change at the global scale, we believe in because there's been a lot of analysis of those phenomena and why they change in the future. And so at the regional scale, it is no different. To actually believe these patterns, we have to dive into them and understand why they have the attributes that they do. And if one formalizes this evaluation process through hybrid downscaling, one also has the benefit of a statistical model that can downscale an arbitrarily large GCM ensemble. And this is important because it provides information about ensemble mean changes and uncertainty estimates that are associated with GCM spread. And understanding key physical processes and ensuring their inclusion in downscale climate projections can in fact